All right, so what I'll talk about today is the idea that consciousness does or does not collapse the wave function. So what am I even talking about here? Okay, so the overview of the talk is as follows. First, I'll shortly refresh your memories. I think most here of you know what the measurement problem entails, but I'll refresh your memory anyway. Then I'll shortly go into the theories about it and why I think that there's really just two options, objective collapse and subjective collapse. And then I'll try to turn up the heat a little bit and say, how can we test, like if I bring you on board that this is a worthwhile thing thinking about, basically, the consciousness collapses idea, then okay, but then how do we actually proceed? So that's the overview. Okay, let me first quickly reiterate what the measurement problem. Do we have a pointer actually? Do you know this?
I don't think we do have pointers actually.
Ah, okay.
We're not told about pointers. So.
Hi, who's he? You're late, man.
Yeah, I don't see pointers here. So
okay, well, I'll just like point with my hand. Okay, so let's just shortly reiterate the measurement problem. I think this is kind of a nice way. I just stole this from Penrose, who explains the measurement problem in this way. So let's say, first let's look at experiment A. And what do we see there? Here, that's the laser. The white thing, that's a beam splitter. And then you have two detectors, C and D. Okay, so this is an experiment you can actually do, and not only you can actually do, it has actually been done. Let's say I set the laser to 1 joule per second. So I just have a burst of 1 joule, then I wait another second and I do it again. What do I find? If I do that, then half of the energy will be at C and half of the energy will be at D. Okay, so that's not very exciting yet, but it could mean two things, right? It could mean that light is a continuous source, continuous wave that gets split in two. So beam splitter splits a signal, 50% goes straight on and 50% is reflected. So if we do the experiment, 50% of the energy ends up in C, 50% ends up in D. Okay, does this mean that light is a continuous wave, or is it discrete? We don't know at this energy level yet, but we can attenuate the laser to, let's say, 10 to the power of minus 19 joule, which is exactly the energy of one photon, depending on the wavelength, of course. And then what we do, we have a burst of this very limited amount of energy. And what do we find now? Now all the energy will either be in C or in D. So per trial, either the whole thing ends up in C or the whole thing ends up in D. And across trials, if we do 1 million trials, it's again 50% ends in C, 50% ends in D. Okay, so this is still not really mysterious. It just means like, okay, so light just consists of particles. It consists of these discrete energy packages, which we call photons. And if we turn it down to the photon level, the photon is forced to either go straight on or go up, and it's just random where it ends up. And if you do a lot of these coin flips, basically, then you get a 50-50 distribution. Okay, but then what happens over here? And before I go on, I would like you, so this talk works a lot better if you think along. Actually, it only works if you think along. So I would like you to puzzle for a second. So again, we have attenuated the laser to 10 to the power of minus 19 joule, so the 1 photon level. And we send 1 photon per trial. And we do 100 trials. So each trial we send 1 photon. We do 100 trials. How many photons end up at detector F and how many photons end up at detector G? And the important thing is the white thing is a beam splitter, so it transmits 50% and it reflects 50%. And the gray things are a complete mirror, so they completely reflect the photon. So I want you to think about this for a second, and then you can inform me what you think will happen. 50-50, yes, of course, it should be 50-50, right? Because let's reason this out. We send a photon, it either goes straight or it goes up. So let's say it goes up, then it's reflected, and then there's again a beam splitter, and it either goes straight or it goes up. So that's 50-50, or it immediately goes straight, and then again it goes through the beam splitter there, and it is transmitted or reflected, so it's again 50-50. If we actually do this experiment, and path lengths are all of equal length, all the photons end up at F. So per trial, okay, yes, at least one person is surprised. That's great. Per trial, you find one photon, of course, but across trials, all photons end up at F. And in a way, that's the measurement problem in a nutshell. So what is going on? How can it be that here we find out it's just a photon? It's a photon that goes up or that goes to C, but here, even though we set it at the one photon level, all photons end up at F. And if you puzzle on this a little bit, what you end up with probably is what quantum physicists ended up with. Okay, basically, what you have is that before you make a measurement, it's a probability wave. So before you make a measurement, it's not a photon yet. Measuring it here in A turns it into, so the probability wave actually splits up. Also here, doing a measurement forces it to show up there or there. Here, we don't do a measurement. So the photon split, the wave splits up and it interferes with itself. And you get negative interference going towards G, and you get constructive interference going to F, and that's why all the photons end up at F. So that's basically the measurement problem. Another way of saying this is like this. So this is just the formalism. So what I'm going to say now is basically a repetition of what I just said. It basically comes down to if you don't do a measurement, so unobserved or unmeasured matter is simply a deterministic wave, completely deterministic, described by the Schrödinger equation. And it doesn't matter, according to quantum physics, how many of these waves you combine. You still just have deterministic wave mechanics. So it's completely deterministic. However, whenever you do a measurement, the wave function collapses. That's how it's called. And you get an indeterministic jump. So rather than determinism is now no longer preserved, and now the wave corresponds to probabilities. And that's basically the measurement problem. So no matter how much unmeasured matter we combine, determinism is preserved. But every measurement, there's an indeterministic collapse of the wave function. And where does this indeterminism come from? Another way to look at so there's actually another way of explaining the measurement problem. So this is the Schrödinger wave equation. And what you will notice here is I. So there's this, it's actually a complex wave function. And that is a little bit weird because we can use complex numbers for making calculations easier, but there are no observables that correspond to complex numbers. So all observables are described by real numbers. So this is a little bit awkward that we have complex numbers in unobserved matter, but when we actually make an observation, when we actually observe reality, these all drop out. So we take the complex conjugates to get rid of the complex numbers. So it feels a little bit like a dichotomy, like when we don't make a measurement, we have complex numbers always. When we do make a measurement, we never have complex numbers. Another thing which is very related, which I'm sure, or I'm not sure, but you may have thought about this. Okay, I'm talking about waves all the time, but what is the medium of these waves? So in actual reality, when we talk about waves, we either have water waves or we have sound waves. They have a medium. Sound waves are in air, of course, and water waves, the medium is water. But these are waves without a medium. So when these kind of waves were first proposed, the idea was there's an ether. But yeah, there's basically all the evidence indicates that the ether doesn't exist. So we're talking about really weird waves here. These are waves without, and that's the same point that I basically try to make with the imaginary numbers. So these are weird waves that correspond to unobserved matter. And the other thing that I want to point forward is that this does not just describe photons, it describes all matter. So the quantum physics, you can do two-slit or these interference patterns. You can do them with photons, but you can also do them with electrons and so on. And I'll give you an example of that later on. I just want to shortly mention this. So you may think, oh yeah, that's just like a mathematical trick to use these complex numbers. And indeed, this was what most people thought. And then this paper came out 3 years ago, which I was very excited about. And this is from a group in France. And they basically showed that in a certain setup, quantum theory based on imaginary numbers, so and the imaginary part only refers to unobserved matter, because there's never an imaginary part in observed matter. Quantum theory based on, which says like, no, we don't have imaginary numbers for unobserved matter, we have real numbers. This makes different, all theories with real numbers make a different prediction in certain experiments than imaginary numbers based quantum physics. So the good thing is all real number quantum physics theories can be falsified. And not only can they be falsified, they are falsified. Because 1 year later, the experiments were really done. And it turned out that quantum physics based on imaginary numbers is true. All real number theories, versions of quantum physics are not true. Okay, so we can reframe the measurement problem by saying, we can just state it like this. So observed reality never contains complex numbers, but unobserved reality always contains complex numbers. So we can say, okay, what is going on? What happens that we go from an imaginary situation to a real situation? This is what happens during a measurement. Okay, so that's the measurement problem. I also want to point out, so quantum physics says this applies to all matter in all quantities. Because we always think like, oh yeah, okay, but that's just at the microscopic level. If we, at the macroscopic level, that doesn't apply. Well, according to quantum physics, it actually does. And in recent years, there have been some papers that have put larger and larger amounts of matter in superpositions. And they're all Nature papers, by the way, because it's very technically challenging. And it's theoretically not surprising, but it's still interesting. And this is a study from 2015, and there they had 100,000 rubion atoms, and they basically just measured an interference pattern, as I just showed it to you, but then not with photons, but with these 100,000 rubion atoms together. And there was no deviation from what you would expect from quantum physics. So it completely conformed to what you expect based on quantum physics. And there's this paper from 2010, also a Nature paper, where they had a 60 micron resonator, a mechanical resonator. And they could show that was also in a superposition. So 60 micron, that's a lot more than 100,000 atoms. It's an insane amount of atoms. 60 microns, you can actually see it with the naked eye. So there really seems to be something going on. All matter, no matter how much you have of it, is described by quantum physics and enters superpositions, but they only leave the superpositions when we do a measurement. So what is so special about a measurement? That's the measurement problem. Okay, and then of course, okay, how do we actually deal with this? And I will say, okay, I'll be very opinionated, so maybe won't like play well with everybody here, but I'll just put it out there. I think there's one way of going about it. It's just basically putting your head in the sand. And I think it's a very popular option, but I think we shouldn't do that. I think we should confront the problem heads on. Okay, so I'm just shortly sketching the main, I mean, there are lots of explanations of the measurement problem. I'll just name a few. So we have the Copenhagen interpretation, we have many worlds, super-determinism, and then you have Bohm, cubism, blah, blah. So I'm not going to go into Bohm. Ian mentioned that Bohm may have some bites, but I won't go into that. I'll just discuss shortly Copenhagen, many worlds, and super-determinism. And the thing with Copenhagen interpretation, or at least maybe I'm strawmanning it a little bit, but I don't think too much, by saying that their credo was basically shut up and calculate. So their idea was like, it works, you know, you shouldn't bother yourself with this stuff. And indeed, when I studied physics, it was generally remarked like, oh, when I brought up the measurement problem, people were feeling a little bit, yeah, it was kind of like, you were kind of like left out of class, and they were like, yeah, are you a philosopher or something? You know, real physicists don't care about this kind of stuff. And that might sound innocent. It might sound like, oh, these are hard-nosed scientists that don't care about this stuff. But I think it's completely mistaken, because it is an empirical problem. I mean, we just observe that that it seems to be that quanta are probability waves, and that they change into something else when we make a measurement. So that's basically an empirical problem. It's not some kind of theoretical problem that people made up. It's not a word game. It's an actual finding that we have to explain. And the other thing is that this attitude of the Copenhagen interpretation has basically stifled progress for a long time. So for decades, nobody basically worked on this. And John Bell's famous theorem was published in 1965 in the journal Physique Physica. So that sounds extremely obscure, and it was also then very obscure. So, and he worked on it in his free time, basically, in secret. Nobody responded to that paper. Shimoni took it up 2 years later or something, also in his free time. So there was this whole taboo sphere around it. But that Bell's theorem is basically it's the main thing on which entanglement, our understanding of entanglements and quantum computing heavily builds on that. So I would say like the biggest breakthrough we had in physics since quantum physics is Bell's theorem, and it was basically done in secret because of the whole atmosphere of it's a taboo, we shouldn't worry about it. So I'm not a fan of Copenhagen interpretation. There's another one which I think is deeply mistaken, is the many worlds solution. So many worlds basically says there is no measurement problem. Why? Because the wave function never collapses. The universe just splits and splits up. And again, like you can make it sound better by saying like, yeah, it's expensive in universes, but it's very economic on formulas or something like that. So like it sounds like something very deep and smart. I wouldn't agree with that. I think it's mistaken, because what they basically say, as I started out, the tension here is that here we see in experiment B, we see all the clicks at F. But in experiment A, we see half of the clicks going to D and half going to C. How does many worlds solve this? They say, no, in experiment A, you actually see a click both at C and D. And it's even worse than that. They don't even say that. They actually say you're in a superposition of seeing both. And I think that's actually an incoherent statement. So I think saying that your conscious experience is in a superposition is an actual contradiction. So you can say like what you will experience is in a superposition and you will eventually experience one of the two things. But saying you currently experience A and you also do not experience A, I think that's an actual contradiction. But if you don't have to go along with that, there are basically no empirical predictions coming from many worlds. So people who adhere to many worlds, it's actually, you may think I'm attacking some kind of obscure theory. It's actually the most popular explanation among physicists. And it's a great way, because now you don't have to think about the problem anymore. It's solved because we have many worlds. And another one that I think also doesn't really address the problem is super-determinism. So I put Gerard 't Hooft there. I'm from the Netherlands. Gerard 't Hooft is like our superstar because he won the Nobel Prize in Physics. He's one of the adherents of retrocausality. So, or super-determinism, I should say. So what does super-determinism say? Okay, because we have this weird particle-wave duality. Here in experiment A, it seems that the photon is a particle. And in experiment B, it seems it acts like a wave, right? So that's what we have to explain. And what super-determinism says is no, actually, the photon is always, 5 minutes, oh my God. Okay, I'll speed up. So super-determinism says it's always either a particle or a wave, but what it is determines the experiment you will do. So if it is a particle, you think you choose to do experiment A, but actually retrocausally forces you to do that experiment. Okay, I think that doesn't work because this kind of retrocausality you can also apply to randomized controlled trials. Now we can't find evidence for vaccines anymore and so on. But the problem with all these kind of things is there are a lot of, I'm like making the theory simpler, but in reality these are like math-heavy theories. There's a lot of formulas, etc. But I think basically what's going on is they bury the problem under a wall of formulas. You don't want to do that. Okay, so I think these are basically all just ignore or deny. I don't think this will help us any further. And I think we should just face the problem head on, and then we're stuck with either objective collapse or subjective collapse. Objective collapse says before, so first we start out with a quantum in a superposition, and at the very end, you will see an unsuperposed particle. Somewhere in between, the transition has happened. Either it's somewhere before you experience it, or at the last moment that you do experience it. If it's somewhere before, it's objective collapse. If it's at the very last moment, it's subjective collapse. Problem with objective collapse is that, quantum physics currently doesn't have a spontaneous collapse factor in there. So it doesn't concur with quantum physics as it is in theory, but also there's no empirical proof for it yet. Subjective collapse, well, it basically implies dualism. It basically implies that consciousness is different from ordinary matter. So it's completely taboo among physicists, but I think it's still worthwhile investigating. Okay, so now I finally get to what I really want to talk about, and I have like 3 minutes left, I guess. How can we, so let's say you go along with, let's investigate this, but how can we actually investigate this? So the first time you mentioned this, I talked about it with actually somebody who got a PhD in theoretical physics, and he just said like, yeah, but can't we just look at the detector to see if it was in a superposition? Well, that clearly won't work, because even if the detector was in a superposition before you looked at it, if you look at it, it will collapse. So we will never see things in a superposition. We can only deduce that they were in a superposition by something like an interference pattern. So that will not work. Now you think like, oh, maybe entanglement will work. So entanglement is of course the idea that two photons are in the same state, or anything are in the same state. Here's just a phi plus Bell state. So let's say I have this idea, I do a double slit experiment. So I have two entangled photons. One photon goes to self-interfere, photon A, and photon B, I either measure it at detectors E or E prime. And the idea here is, if I measure B before A self-interferes, there cannot be an interference pattern, right? So let's say I measure B at E prime, then A collapses to one of its paths, and because it only takes one path, it cannot self-interfere and there will not be an interference pattern. And likewise with, if I measure it at the other location, and if I don't measure it, A can self-interfere and there's an interference pattern. So now I have a dependent measure. This will not work because entangled photons do not produce a local interference pattern. So I got the actual derivation of this in my other slides, but it's pretty easy to show that actually in this setup, there's no local interference pattern. So A will 50% of the time go to D or D prime. So this whole thing of it just goes to F is gone. And the same for B, and there's also no global interference pattern. So there's also no conditionality between them. And anyway, if you go through it, bipartite entanglement will never allow you to solve this thing. Bipartite entanglement, so you have the no signaling theorem. So if A and B are entangled, as A itself, you cannot see if B is measured or not. And the way to think about this, let's say we have two coins, and they're completely correlated. So if this one is heads, then this one is also heads. And if this one is tails, then this one is also tails. Locally, it looks like 50-50. But globally, if I put the results together, I see, hey, they were completely correlated. But it doesn't matter. And the other thing is, it doesn't matter which of the one I measure first. So if I measure this one first, it will determine what happens here, and vice versa. So I will see a complete correlation no matter where I start measuring. So this is now, can I eat into my question time? I'm already eating into my question time, okay. Then I go to what I think is the most promising approach. So I'm not sure it will really work, but I definitely hope so. So let's say we have A and B are entangled and C and D are entangled. And now there are two possible scenarios. So scenario one is B and C interact, and then we measure A, B, C, and D. So in this scenario, we have first a complete multipartite entanglement, and after that, we measure all the particles. The other option is A and B are, so we are in A and B are entangled, C and D are entangled. We first measure A and D, then we let B and C interact, and then we measure A, B, C, D. And the question is, are the global correlations the same in both scenarios? So I guess it's a lot of information to take in, but I'll just throw it out there. And so to say it in other ways, so let's say we have B and C interact before T1, and T1 is when the information reaches your NCC. Or we have BC interact after T1 is reached. Then the idea would be we get different global correlations in both scenarios. If it's true that the everything entangled scenario has different global correlations than sequential bipartite interactions. So I don't think everybody followed that completely, but yeah, I'll finish up. The funny thing is that the thing that I propose here is basically the same as a scenario that Renou et al., when they had the thing about quantum theory based on real numbers can be experimentally falsified, they had that scenario. They basically had the entanglement swapping where they used, so it's basically a scenario that I just sketched. And they basically said every bipartite entanglement can be described by real numbers. And their entanglement swapping scenario requires complex numbers. So then the idea would be like, if that's true, then if you first measure AD, then you only have sequential bipartite entanglements, which suggests to me can be described by real numbers, but I'm not sure. And I just want to, this is the last formula I put out there. The idea, what are we looking at here is, the idea with complex numbers is simply, if you don't have interactions, it is the same, the order of measurement doesn't matter. But if you have, and that's the important part here, A plus B complex conjugate squared is not the same as A squared plus B squared. So there's an interaction term. This is basically an interference pattern. And the idea that I'm interested in is there some kind of second order interference pattern if AD and BC, between the entanglements of AD and BC, if we do the global versus the sequential scenario. So just to, now I'm really finalizing. So let's say the scenarios are different. That would be great, because then we have a measurement, then we have a way to test if consciousness collapses the wave function. I think it's also fun if we find out that the scenarios are the same, because then it means we can do all multipartite states can be construed through bipartite interactions. So if the two scenarios are the same, then we can do all the math on multipartite interactions through bipartite calculations, basically. And then we'll greatly simplify the math, which is important for quantum computing and stuff. Okay, so I'm gonna open up the floor for questions, but before I do that, so this is work in progress. I don't have the answer. If you are interested in this and you think you can contribute to this, please let me know, because I'm actually looking to set up collaborations about this to, push the ball forward, basically. All right, well, that's it. Thank you.